All right. So we're going to start right now with stuff about vectors. So we're going to leave matrices just for a really short time and talk about vectors, which are really, really essential to understand the big picture. Is there anybody here who is not in or has not had Calc 3? You decided to do them out of order. Okay, so everybody in here has some vector exposure, whether it's currently or in the past. It is not necessary that you know anything, but it is very useful, obviously, if you have some information, because what you were told was factual. We're going to be looking at vectors from a different point of view, though, in this course, because we're also looking at multidimensional stuff. So we're talking about vectors, okay? We have some very, very basic definitions. So if I said vector U okay, let's say it has n components, then we would say vector U is an element of that. Does anyone know how to say that? In Calc 3, you should know how to say it. No, just what is that symbol?
Span?
Rn. What is the xy plane? That's R2. What's the XYZ space? That's R3. That's how we say it, just so you know. Now, why do we put an exponent in that position? Has anyone here completed discrete math? I know you're in it. Have you guys got to Cartesian products? Were you in my class?
No.
Oh, okay. Cartesian products is when you take one set and you match it with another set. So if I take the set of real numbers, that's cross product in vectors, and a Cartesian product of sets are basically the only time you ever use an X in math since you were little kids. You don't use it for multiplication anymore. And so if I take a set of things and I do a Cartesian product with another set of things, I get a set of ordered pairs of those things. If I do another one, I get a set of ordered triples, and so on and so on and so on. So R2 is the real numbers crossed with the real numbers. R3 is cross, and so on. So we say Rn, or n-dimensional space. But space is kind of vague, because space generally is three-dimensional. So we just say it's n-dimensional. So all the components have n dimensions. That's it. No big deal. But we need to define it. So when we say Rn, we're saying it could be any dimension. We're not being specific. In Calc 3 and in physics, you almost exclusively in R3, because we live in a 3D world, everything before Calc 3, it's R2, right? But everything's XY plane. So the XY plane is called R2. Now, is it possible we could be working with complex numbers? Yeah. Then we would use the script C. Now, we aren't going to do that until the very, 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 very end of the course, but you'll get a glimpse. So don't even worry about that. So this is Rn. So now the very first thing we do is we say if vector U and vector V are elements of Rn, that means in English they are the same dimension, then U plus V is defined as, now with that, let's define V first, just to make sure. We'll call that V1, V2, Vn. This is defined as, 3 bars is not a result, that's the definition. So the nice thing is you don't have to prove that. This is what it means to be a sum. It's U1 plus V1, comma, U2 plus V2, comma, all the way to Un plus Vn. So we define the sum of vectors as being the vector of the sum of each corresponding component. So the very first and most humongously significant rule is you can only add 2 vectors that are in the same dimension, because otherwise you have incompatibility. We talked about matrix multiplication earlier after we defined it. You can't multiply all matrices, can you? Can you add all matrices? No, they had to be the same size, same dimensions in order to perform that. And then once, if they are, then performing it's a piece of cake. So this is easy. But U1 and V1 are real numbers. Now, a vector can have functions in it. In this course, there's going to be a couple times we'll look at functions, but for the most part, vectors are going to be scalars inside the vectors. Okay. But whether they're scalars or scalar valued functions, we know addition of scalars or scalar valued functions is commutative. So then I know this is V1 plus U1, V2 plus U2, on and on, Vn plus Un, And why is that important? Because this is v plus u. So this is the proof of one of the really important vector properties. Vector addition is commutative. Now, all of you knew that from other classes, but that's actually how you prove it. Now, what about associative? If I took 3 or more vectors and added them, I'm adding the corresponding correspondents, which are real numbers, and I can, of course, use associative property to regroup. Yeah, it's also associative. That's really, really simple to work with. I am not interested in the geometric properties of vectors right now. You know, where I'm going to draw the picture and I'm going to show the vector on the other end of the vector. Yeah, I can do that in R2. What if these are in 7 dimensions? I'd have a hard time drawing this one. You know? So don't worry about the geometric interpretation. I just need to know that. So there's basically 2 operations we can perform with vectors. Obviously, vector addition being one of them. What's the other one?
Multiply by scalar.
Scalar multiplication. Now, that one is always a little bit tricky. So that's vector addition. Say scalar mult. This is where scalar actually makes more sense to people. If you thought of a map, okay, I use Google Maps. I'm one of these people, I will use Google Maps and I will look up something and I will look at, you know, at the time of day, what's the fastest route, kind of say, you know, traffic. Oh, but let's say there's no traffic. I just will take the shortest, simplest route. And I'll look up and I'll say, okay, I'm familiar with this. The rest of my family, they love to use their cell phones and punch in something, and I don't know why. I won't mention any particular names, but my spouse. We get lost 100% of the time when she uses the app on her phone. It will literally send us in the opposite direction, or it's across the street. Why are we going that way? You know, it's incredible how bad technology is when it comes to, you know, when you're on the move. I mean, oh my goodness, I can tell you stories. We're trying to get to the gas station that's across the street, and they'll use, well, let's use the car GPS. You know, 15 minutes later, we're at a gas station on the other side of town, but there's one right there, but it took us 10 miles out of our way. I have fun with that. If I'm looking at a map, okay, say, wow, I'm looking at a world map, and that other country's only 3 inches away. Maybe an inch represents, you know, 10,000 miles. I don't know. There's always a legend, isn't there? In other words, that tells you, you know, 1 inch is represented by this. Or 1 mile is represented by this short distance. You have to look at the legend because the map is small. Okay, it is scaled down appropriately. Now, the scaling is actually very important. Okay, I like to use Thanksgiving Day, right? Thanksgiving Day, you turn on the TV, what do you see? Lots of parades, right? And you see the, you know, things floating around, you know, like the Stay Puft Marshmallow Man from the first Ghostbusters movie, right? Gigantical versions, those are scaled up. A scalar is basically a multiplier that preserves everything, all ratios and so on. So we're finally gonna make that statue of Brian out in front of the campus. You know, the one where you're on the horse, you know, and you've got your hand tucked in, whatever, you know, and you've got the sword. And so what we're gonna do, how tall are you? About 5'7"? 5'7", okay. We're gonna make an 11-foot, 2-inch statue, double your height. But we weren't paying that much attention, so we made your head the exact same size as it is now. But your arms are a little bit longer than double in this day, kind of, you know, Neanderthal. And in other words, we didn't preserve ratios very well. That is not a scale model, is it? In other words, it is not to scale. By the way, if it's not scale, there's only one word in the English language that is used. We say it is distorted. How many have been to a fun house before? Everybody look, you know outside the mirror? You got the mirror, your head's going weird. And by the way, every guy on planet Earth, look away, don't let them know you're looking at them, but every guy on planet Earth will, you know, roll up his sleeves a little bit, get his arm positioned just right, right? Why? So you have the biggest biceps in the history of the world, at least for a second. Be honest, you've all done it. Everybody does that. This mirror does not preserve any form of ratio. It is called a distortion. A scalar preserves everything. That's why we use the word scalar. And that's not a light term, because there's a lot of times we do stuff or we change stuff. And we do stuff, and there's words that we do. We can change vectors by distorting them. In fact, at the end of chapter 6, the author does these kinds of things. And because sometimes that's useful. But a scalar preserves, so all I have to do is, if I take k times vector v, I get ku1, ku2, all the way up to kun. So every single term gets multiplied by the same amount. So if I was talking about a physical vector that I can measure, one in R2 or R3, this basically will just extend it or shorten it on the same line that it currently lives on. That's important, because if I don't have the exact same coefficient in front of each of these terms, that vector will point in a different direction now on. So in other words, I won't preserve that part of the vector. So scalar multiplication, absolutely trivial. There's absolutely no part of this that should really give us any issues. So, with that said, the term linear combination. Many of you have heard this term in other classes. What exactly does this mean? A linear combination would be something like this. I have, I'll say A as a constant. I have A times vector U plus B times vector V. I have a scalar multiple of each vector, and I'm adding them together where there is no restriction on the scalar. It can be positive, it can be negative, it can be zero. This is called a linear combination because, again, it's kind of lame in this sense because you can't square a vector. I mean, you can't take a square root of a vector. You can't take the sine of a vector. You can only add them or multiply them by scalars. So a linear combination, the linear is easy. If I was talking about functions in Calc 1 or Calc 2 or Calc 3, a linear combination of functions would still be a scalar multiple of each function because I could square a function, couldn't I? I could take the cosine of a function. But the linear part means no, scalar multiples are all that's allowed. So in other areas of math where I can manipulate more, linear combination means the same thing. So let's do something real simple. Let's suppose vector u is 3, negative 4, 5, and vector v is negative 2, 1, 6. All right? I want 4u minus 7v. And the result is a single vector. Just simple exercise. So, the easiest way to do that is, well, what's 4u? That would be 12, negative 16, 20, plus, never subtract. Why never subtract? Because the only number you're going to have right is the first one. You know that every number after that, you're going to forget to distribute the negative. How do I know? Because I've taught tens of thousands of students, and I teach the smartest people on planet Earth, and they still always forget to distribute the negative. No, multiply by negative 7. So then it's 14, negative 7, negative 42. Much easier to do this. I don't have to think. Now, there's nothing special about the answer except that's a linear combination of those two vectors using those coefficients. That's it. Well, that was pretty easy. Okay, that's supposed to be fairly simple. Now, sometimes we can have a problem that's a little more complicated than that. And I can ask something like this. I can say, let me start with, how about V1 is 2, negative 3, 4. V2 is negative 1, 4, negative 6. V3 is about 0, 5, negative 2. Okay? And now the question I might want to ask is this. Consider W, and let's make it real simple. Let's say that W is 3, negative 7, 0. Is W a linear combination of V1, V2, and V3? That's my question. Okay? Actually, no, I'm going to change this. I'm going to make this better. Okay, make it a 4. That's way better. Okay. How do I answer the question? What do you think? Give me a starting point.
Can we make 3 equations out of the vectors, because 8 times v1 plus b times v2?
Okay, so let's start with that. I like that. So actually, there's a certain notation that you're probably all going to get really comfortable with really quickly, and it's not a rule. It's just that all the textbooks do it the same way. When I have arbitrary constants, textbooks love to use C's. When they have more than one arbitrary constant, they love to use things like, C1, C2, C3. So almost every book will do the same thing. A, B, C is fine. They'll say, how about if I write it like this? Now, I don't care what letters of the alphabet. I like the 1, 2, and 3, because then I know which one it goes with. To me, that's convenient. Writing A, B, C is fine, but then it's not as clear which one goes with which one. So if I do this, what will this look like? Well, that will give me a system of equations, won't it? So, first case it would be 2C1, negative 3C1, 4C1, plus negative C2, 4C2 minus 6C2, plus, I'm going to write 0, C1, just so I don't lose my space here. Where are we on? 5C2, negative 2C3. Did I write that correctly? That's a 3. And then that's all supposed to equal W.
Shouldn't it, the second one be all 2s and then the third one all 3s? No.
What did I do?
For the constants?
Oh, yes, that should be 3s. Thank you. That's why I asked the question. That is, I had it right the first time. That is a 2. Now, get the numbers 2, negative 3, 4, negative 1, 4, negative 6, 0, 5, negative 2, and does that equal this? Okay, well, God, there's still more to do. Oh, but wait a minute. Vector addition is defined by adding the first components. Could I make it easier on myself and say, let me take the first component of this, plus the first component of this, plus the first component of this, and set it equal to 3. Would that work? Yeah, because that's technically what I want to solve. Oh, then let's do the same thing for the second components. Make sure I don't get these wrong. I would get it wrong, and then that equals negative 7. And then the last component would be 4C1, negative 6C2, negative 2C3 equals 4. If I wrote this correctly, I have a system of 3 equations and 3 unknowns, don't I? Oh, can I use a matrix to solve this? See, my unknowns are the coefficients. I think we all agree with that. So what if I now write this? Let's write it as a matrix. Whether I write it as a matrix product, or I just simply do row operations on a matrix, I'd be inclined to just simply do row operations on a matrix. I think that's probably going to be the least effort. Okay? So I'm going to write it down 2, negative 3, 4, negative 1, 4, negative 6, 0, 5, negative 2, 3, negative 7, 4. Beautiful. What does the first column represent?
First vector, V1.
Well, I'm trying to solve for C1. Agreed? Everybody agree? I'm trying to solve for C1. But what are the coefficients of my first column? Huh. Do you notice something really interesting here? We might have been able to expedite this process a little bit faster. But you need to see it first. The most important thing I need to do, start the problem. I want you to see this though. If you all agree this is what I'm trying to solve. This produces a system of equations which produce this matrix. And notice where the vectors ended up in the matrix. In this case, they all ended up as columns. And the reason is a linear combination of these columns produced the last column. Vectors do not always end up as columns. They end up as rows just as often. But if I understand that, oh, because I'm doing a linear combination of these vectors and then my last column is the W, I could have just gone right to the columns. And again, over time in practice, that becomes an easier thing. Can I solve this rather simply using a matrix? Sure. What do you want to do first? I don't have a good pivot. What if I add row 2 to row 1? I'll put a negative 1 there. Negative 1 is just as good as anything else. So how about row 2 plus row 1? So then I'd have -1, 3, 5, -4. Then I'd have -3, 4, 5, -7. You know, I could do a determinant, there's nothing wrong with that. So now I've got my perfect pivot. So I'm going to go -3 row 1s plus row 2. So 0, -3 of those, that'd be -5. -3 of those, that'd be -10. -3 of those, that would be 5. I'm going to go 4 row 1s plus row 3. So 0. 4 of these, that would be a 6. 4 of these, that would be an 18. 4 of these, -6, that would be -12. I could add row 3 to row 2. That would work fine. But I could also multiply row 2 by a fifth or negative a fifth, couldn't I? Does it matter which one I do? No. I'm going to multiply. So I'm going to go -1/5 row 2. So 0, 1, 2, -1. Yeah, I can multiply the last one, but why? I'm going to put a 0 there on the next step anyway. So my next step, and by the way, I could go up and down or I could just go down. Which way do you want to go?
Up and down. Up and down.
Okay, Zachary says up and down. If I'm going to do that, then I probably wanted to put a 1 here. I probably would have wanted to multiply, so I'm going to be lazy and just go down. Do you understand? If I'm going for reduced row echelon form, then I kind of need a 1 in that other position, and we didn't go that way, so I'll just do this. So -6 row 2s plus row 3. So 0, 0, -6 of these, that's -12 plus 18. +6 plus -12 is -6. That's what I need. So we'll now go back substitution. So the last row says C63 equals -6, so C3 is -1. The second row says C2 plus 2 times C3 equals -1, so C2 equals +1. And the first row says -C1 plus 3 times C2 plus 5 times C3 equals -4. So that means that C1 equals 2. Okay? Am I done with the matrix part? Yeah. By the way, I don't have a way of checking yet. We will check. So is my answer an ordered triple? No, my answer is a linear combination of vectors. Oh, I used the matrix to solve the system, but I'm not looking for a point in space here. I'm looking for the coefficients of my linear combination. So it appears that my answer is what? Tell me, what would it's 2, 1, -1? So it appears that I'm claiming W equals 2V1, again, plus 1, 1, plus V2 minus V3. Does that make sense? That's the answer to my question. Easily enough to check by just checking the coefficients. The check can be anywhere. It can be here, it can be here. It doesn't matter. I think it's going to be okay. So I've just written W as a linear combination. Is it possible that this was an inconsistent system? Is that possible? Absolutely. Is it possible that this ended up a dependent system? Yes. But in this case, the question was, can I write it as a linear combination? The answer was yes, and we did. So the final answer to the question would just look like this. I don't need to restate these guys. I've already got them. Okay? So that's just a simple algebra thing. Okay? Everybody cool with that? Now, vectors are very interesting creatures in that they have a lot of properties that act like real number properties. And we talked about this at the beginning with matrices. Okay? In algebra, there are 11 things that I can do in algebra to manipulate. If I have an equation, for example, we have addition and multiplication, right? We have commutativity, associativity, identity, inverse, and the most important one, closure. And I have the same 5 for multiplication. What's the 11th property? Distributive. That's the one that crosses over both of them. And these are the properties of things I can do with real numbers. So if I had a simple equation in baby algebra, and again, I remind you, because let's suppose you were tutoring somebody in a lower level algebra class, and let's keep it really simple, you know, and they're doing, 3x minus 7 equals 12. They're solving this problem here. But they're novices to math. They don't really know what to do. And you say, well, I want to get the x by itself. So first of all, do I undo the addition first or the multiplication first, or does it matter? Actually, the rule of thumb is you always go by order of operations and you do it in reverse. You always attack the weaker operation. When I would teach remedial algebra, I'd say it like this. Okay, we're gonna go tiger hunting. We just watched Gunga Din and Jungle Book for the 10th time, and Shere Khan, oh yeah, we own him. So we go, and of course Shere Khan shows up, and he's a lot bigger in person than he is on the screen. And so he immediately jumps on Shere Khan's back, and you grab him around and you just hang on for dear life, and I grab his tail as he's running through the jungle. Now, he's only hungry enough for one of us, by the way. Who's he going to eat first? The person grabbing onto his back or the person dangling from his tail? Well, which is going to be easier to get rid of? In other words, you're the multiplication, I'm the addition. I'm the weaker operation, he's going to eat me first. Okay? Whenever you solve, you always go in reverse order, in other words, because if you go in the higher order, you end up creating more steps rather than making it easier. So, we're going to get rid of the addition. So I can add any real number to both sides. So I decided to add pi to both sides just because I thought it would be really cool. Is that legal? Yes. Is it useful? No. So what are you going to add to both sides? Well, let's see. You're going to add the additive inverse of this, which is positive 7, and you're only going to add it to the left side. No. You're going to add to both sides because that's the addition property of equality. If you want to preserve an equation, you have to do the same addition to both sides. Oh, okay, so I add to here. Now, do I put the 7 on this side or do I put it on this side? Doesn't matter because addition is commutative. Okay, so now technically I have this, but I really want it to be this. Can I do that? Yeah, because addition is associative. And when I add negative 7 to 7, I'm going to get what? 0, because that's the additive identity, which is what happens when you apply an inverse. Okay, so now my left side is 3x plus 0, which is now 3x. We actually used 5 different properties of algebra. There's actually one more, I'll mention later. We used the addition property of equality, associativity, commutativity, additive identity, and additive inverse just to get the 3x by itself. And what's on the right side? 19. Now, when you're doing this, are you doing this as 5 independent steps? Are you doing it as one step? And someone says, how can you do that? You say, because I did all of those things, but I can do all those things legally by just adding 7 to both sides. But why 7? Because it was the additive inverse. I could have added any real number, but any real number would not have been useful. That's the most useful. And so, in other words, for me to perform this legally and get a right answer, everything I do has to be a correct legal operation. I want to be the most efficient, so I do, obviously, the next thing I'm going to do is multiply by a third. Why am I not going to divide it? Because there's no commutativity, associativity, identity, inverse, or closure, or division property of equality. Actually, there are no algebraic properties whatsoever that apply to subtraction or division. Those are artificial, made-up operations. Why? Because when you're little, negative numbers are really hard to understand, so we introduce subtraction. Fractions are hard to manipulate, so we introduce division. But there actually are no mathematical properties for either one of them. Not a single one. A divided by B is not B divided by A, although we sometimes get in trouble with that one, don't we? A minus B is not B minus A. Everything fails if I try to apply any of those properties. So you don't divide and multiply by the reciprocal. It's way easier that way. And then you don't have to worry about it. You can accomplish everything, but that's a higher order of reasoning. Now, my result is the key. What am I going to get as a result? I'm doing real number operations. I'm going to get a real number back. I'm not going to get an imaginary number. Do you agree? Are there mathematical operations that can mess that up, that don't preserve the real number answer? Tell me the simplest operation where you can lose that.
Zero.
What operation?
Square root.
Square root. Perfect. Oh, if I apply a square root to a negative number, I will introduce imaginary numbers. So do all operations preserve what you're working with? Actually, no. A lot of them don't. So the next thing I want to introduce is the concept of closure. This is the most important of all the properties of real numbers. And it's one that I talk about this in my remedial classes. I introduce it, you know, a little bit maybe in calculus. We don't dwell on it, but we need to dwell on it here because it turns out it's the most important. The concept of closure in simple English is, if I take any two elements of the same set and I combine them using whatever operation you want to use, whatever the operation is, could be exponentiation, could be take a cosine, it could be division, it could be multiplication, but whatever operation I'm using, I'm guaranteeing the result is still in that set. And that is not an automatic thing. For those of you who know dot product, if I take two vectors in the same dimension, I can do a dot product. And therefore, when I take two vectors in the same dimension and I do a dot product, then of course I get back a vector in that same dimension, right? What do I get back? The scalar. Oh, that fails closure about as badly as you can fail closure. Oh, in fact, most everything you could possibly do in mathematics fails closure. So we want to talk about when it's satisfied. So let's start with addition. And the easiest way for me to demonstrate this is, let me use the number groups, okay? The natural numbers are the counting numbers, right? 1, 2, 3, 4, 5. We call them the natural numbers because when you go outside and you're counting things, you don't count, well, there's only a half of that one, there's only 3/4 of that one. You say 1, 2, 3, 4. The natural numbers are counting numbers. If I throw in the 0, then I have the whole numbers. If I consider every positive and negative value, then we have the integers, which up to Calc 3 you use the capital I, but now it's the right I wink. What's the symbol we now use? It's like the secret handshake.
Z.
Z. When I see a student use Z for integers, like, haha, they know. It literally is the secret handshake of mathematics. If you use a capital I say, oh, that's nice. You know, that's very nice. But when you use the Z, I'm like, you know, it's like the secret handshake, everything. You know, backdoor pass. Why do we change the symbol around now? I have no idea. But in discrete math, you use a Z. Sometimes in Calc 3, that's kind of the borderline. But by now, this class, differential equations, you use a Z. Now, if I consider every conceivable quotient of integers, every conceivable quotient, that's basically the definition of a fraction, by the way. A quotient is not a fraction. A fraction is a quotient of integers. Use a big Q, and those are called the rational numbers. The rational numbers. A rational number is any number that can be written. So is an integer a rational number?
Yes.
Yeah, you have an infinite number of representations of any integer. Heck, take 1. 1 over 1, 2 over 2, 3 over 3, 4 over 4. Those are all equal to 1. But they're all written as quotients of integers. So every integer could be written as a quotient of other integers. We know that. Now, this is where it gets a little bit dicey. So you have to remind yourselves, and if I was teaching discrete, I would be going over these same concepts. Every rational number, if I think about it in decimal form, there are two possibilities for a rational number in decimal form. I'll use the simplest two you can think of. How many more 3s?
Yeah.
Like 4 more? So what do? We usually do something like this. Every rational number either has a terminating decimal or an infinite repeating decimal. That's the key. It's got to be repeating. Yeah, if it's not terminating, it's infinite. But it's got to be repeating. That's an alternate definition of the rationals. Thereby, I'm able to define the irrationals as every number that has an infinite, non-repeating decimal sequence. Pi, square root of 2, e. You with me? Oh, okay. So every number either is terminating or infinite in decimals. If it's terminating, piece of cake. It's a rational number. In fact, if you gave me any terminating decimal, it will take me 1 second to convert it to a fraction. Think about it. Just move the decimal, put it over, 10 to the right power. You learned how to do that as children. If you give me any number and you tell me it's repeating pattern in Calc 2, I remind you, we did that with geometric series. You can actually tell me what that is. But if I gave you a number and I gave you the decimal sequence and I said, well, it's an infinite non-repeating decimal, it's rounded off to here, it's not possible to say where it came from. So that's kind of icky. So every decimal representation is one of these. Now when I put these two together, of course, I get the reals. And that's where we use the script R. Now, if we keep going, which we actually have to eventually do, we don't in Calc 1, 2, and 3, except for the hyperbolic functions. We barely touch them. For every real number, if I slap an I on it, I get an imaginary number. So we know that. We usually use IM for that. There's exactly the same number of imaginary numbers as real numbers. For every real number, take that real number I. Now, we're not going to talk about complex numbers in this class until the very end. But if I put these two together, I actually have the granddaddy of them all, and that's the set of complex numbers. We don't spend a lot of time in the calculus and below talking about those, but they're there. We'll get to them later on. And it's very important we understand this. Let's talk about addition. If I add any two natural numbers together, do I get back a natural number? Yes, that's an axiom. Axioms and postulates are essentially the same thing. They try to tell you they're different in high school geometry. They're basically the same thing. An axiom or a postulate is an absolute truth that cannot be proved. Okay? Why can't it be proved? Because it's a building block. It's a starting point. I have a point. I have another point. Exactly how many lines can I draw through these 2 points? One. You know that. That's like duh. Oh, by the way, could you prove it? Nope. It's a starting point. It's an axiom. It can't be proven. It's the very, very, very beginning, and then I can build from that. Okay? If I add any two whole numbers, still whole number, yeah. How about rational numbers? If I add any two, in discrete math, that's one of the very first proofs you learn how to do. It's a cool proof. You take anything that can be written as a quotient of integers and you show by adding it your result is a quotient of integers, but you have to assume the set of integers is closed to addition to begin with. You cannot prove that this set is closed to addition. It's an axiom. It's a starting point. If I add any two integers, I'm always going to get back an integer. I accept that as proof. What's the difference between an axiom and a theorem? A theorem is an absolute truth that has been or can be proved. See the difference? And how do you prove theorems? You use previously proved theorems, definitions, axioms. You put it all together, then you get bigger and bigger and bigger things. If I take any two irrationals and add them together, of course, I take pi plus root 7. Duh. I take any two irrationals and add them together, oh, wait a minute. By the way, if you take any interval of real numbers, there are more irrational numbers in that interval than there are rational numbers, the whole number line. When you get into discrete math, you actually talk about orders of infinity. Wait, there's something bigger than infinity? Yeah, there's countable infinity and there's uncountable infinity. Yeah, that's countable infinity. I can go 1, 2, 3, 4, 5. It's going forever. That's uncountable. As my kids like to say. So is that like infinity squared? Probably more like that, yeah. I just showed you two irrationals that added to a rational. I don't need to do any more, because that's always be true. The set of irrational numbers is not closed to addition. Real numbers, yes. Imaginary numbers? 0 is real. 0 is not imaginary. Oh. So, two of the biggest important number sets are not closed to addition. That's kind of important. Are there any finite number sets that are closed to addition? That's a tricky one. If I gave you this, here's my set. Is this closed to addition? Take any two numbers, add them together. Well, 1 plus 1 is 2, but 1 plus 2 is 3, and 2 plus 2 is 4. Oh, it's not closed. In fact, there's exactly one set, one finite set of numbers that's closed to addition. It's not very exciting. What do you think, guys? Yeah. That's the only one. Well, that's kind of boring. Yeah, finite sets generally cannot be closed to addition. So we're only dealing with infinite sets. Now, that's the concept of closure. Now, if I was talking about multiplication, not scalar multiplication, just straight up multiplication. Basically, it's the same thing. Multiply, 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 and again, that's a discrete math proof. Okay, well, obviously, if I multiply pi by root 2, duh. So let's, I multiply root 8 by root 2. Oh, it fails again, doesn't it? Yep, irrationals are not close to any form of multiplication either. How about imaginaries? That's the easiest one of all. AI, A is real, so AI is imaginary. Let me take a different imaginary number. How about BI? What do I get? Yeah, imaginary numbers fail closure as bad as you can fail because the product of any two imaginary numbers is real. Fails pretty badly. But these two sets are closed to everything, reals and complexes, and that's really, really important later on down the road. So the concept of closure is just this. I want you to get an idea, because we're going to be doing it mostly. The big three that we're going to do this stuff with are matrices, vectors, polynomials. Those are the ones we deal with over and over again because they're really easy to conceptualize. It's incredibly practical because that's what we work with mostly. Okay, any questions so far? All I've been talking about is just very, very basic properties of vectors. Now, in the textbook, the author gives a very thorough list. Where is it? In section 4.1, here we go. It says properties of vector addition and scalar multiplication. And all of these you would know. There's just, I can distribute a scalar into the sum of two vectors, little things like that. Just really, really easy stuff. Okay? Absolutely no issues. So now, vectors have certain properties. We need to know their properties inside and out. We can't question it. If someone asks you, can you square a vector? No. Can you divide with vectors? No. Can you take the square root of a vector? No. Can you add them? Yes. Can you take scalar multiples of them? Yes. Can you add scalar multiples of them? Yes. That's a linear combination. That's pretty much all you can do. Okay. You're thinking, what about dot and cross product? No, those are artificial operations that we made up. Like matrix multiplication, we made it up. We set the rules so we'd have a consistency, but the addition and the scalar multiplication are the only natural operations that pre-exist. So, okay, I have this set of things, and it has a lot of the vector properties. How can I treat that? So, here's what's going to happen. Okay, my first name is Michael, because you didn't know that. Most of you thought it was Mr. or Professor, but it's actually Michael. And I decided I'm going to start my own club on campus. It's going to be called the Michael Club. Now, I have a long charter, and it's very, very important. You have to read the rules and regulations. First of all, 4-day weekends, okay? The three most important letters in the human language, I, P, A. Wings are a food group. Hockey is second to none except for maybe football, okay? MJ is still the best. LeBron and Kobe are fighting for that number 2. I mean, there's a really serious set of rules that you have to follow. But I forgot in the charter, I forgot to mention that your name should be Michael. So Steve was looking at it going, that's me. All of these things are me. Allie's going, you just described my entire life story. And Stefan's like, same thing. In other words, every single one of these things that needed to be, you're there. So you are now in the club, even though your name's not Michael. I'm describing verbatim the most abstract thing you'll ever deal with in your life. It's called a vector space. A vector space. Vectors have a certain set of rules. They have a charter. You want to be a vector? You got to satisfy those rules. What if you satisfied all of those rules exactly, but you're not exactly a vector? See, you might be a matrix. You might be a polynomial, but you satisfied every one of those rules. Then we call your set a vector space, even though you aren't vectors. You're in the Michael Club, even though your name isn't Michael. You understand what I'm getting at? A vector space is any set, it's going to be infinite, but any set where all of the properties that we establish for vectors, it satisfies in its own way. Matrices are a biggie. Polynomials are a biggie that do this. Now, why is that important? Because if they satisfy all the properties of vectors, then all the conclusions I can make about vectors, I can eventually make about these guys. Later on, it's not that far in the future, but later on, we're going to be doing some crazy cool stuff in here. In other words, I'm going to show you how to do a dot product between polynomials. I'm going to show you how to take the determinant of a vector. I'm going to show you how to integrate, find the antiderivative, evaluate it, of a matrix. What? If the situation is right, one of these has all the same properties as the other ones, conclusions about one, but they're at different places in the universe. They're bazillions of miles away, but I'm going to show you a little wormhole. I'm going to show you a way of connectivity. Now, it makes no sense at all to say something like a determinant of a polynomial. No, but if I showed you that polynomial acts the same as a matrix, which acted the same as a vector, there's certain things that I can do. As long as I can prove these things are isomorphic. You remember what that word means? Same form. And that becomes the most important goal in this class. If I can show two things have the same form in their vector spaces, then everything that's true about one gets true about the other, even things that don't even make sense, determinants, integrals. We can do this. And entire branches of mathematics are based on this. Entire conclusions, big conclusions, are based on this kind of stuff. And it's, like I said, it's crazy cool. We're going to answer questions that not only aren't that easy to answer, we're going to answer questions that you didn't know there was actually a question there. We're going to discover there are questions you never thought of, but you'll be able to answer them. It is wild. So to be a vector space, you have to satisfy all of the properties that the vector has. So, now, let's say, for example, I'm going to start with something really simple. Let me call W the set of all vectors of the following form. 3s minus t, 2s plus 4t, 2t, such that s and t are real numbers. So this is an infinite set, do you agree? This is an infinite set of vectors. I would like to know if this set is a vector space. So what we would do is we would go through all of the properties one at a time. For example, if I took two random vectors in this set, if I took W1, well, let's call W1 3s1 minus t1, 2s1 plus 4t1, and 2t1. And let's take a second vector, call it W2, and we'll make that one 3s2 minus t2, 2s2 plus 4t2, 2t2. Here's two arbitrary vectors in this set. Now you notice how I wrote it? So they have exactly the form of a vector in the set. You can pick any real numbers you want for the s's and t's, and that vector will be in the set. So the first question is the sum of these two vectors in this set? Is every scalar multiple of these two vectors in this set? If I took a third vector, will it satisfy the associative properties, and so on? This is how you prove something as a vector space. It can be really tedious. But I don't like to waste a lot of time because, quite frankly, if something satisfies certain properties, it's actually always going to satisfy the rest of them. I'm going to show you that over the next couple of days. So you don't really have to go through all 10. That's an exercise at the beginning that everybody makes you do just so you understand them all. But it is kind of a waste of time. There's really a big three. And this is the primary point of next day's lecture while we're at it. The big three are the closures. Do I satisfy closure of addition and scalar multiplication? Because those are the biggest ones. But secondly, there has to be an additive identity in the set. Now, a lot of people just generically say there has to be a zero vector. If I was talking about matrices, there's no zero vector. If I was talking about integrable functions, there's no zero vector. If I was talking about polynomials in general, there's no zero vector. So I don't like using the term zero vector, just say additive identity. Now, if I was talking about a bunch of vectors, then the additive identity is the zero vector. We know that. Okay, I didn't spend time talking about that because I know all of you guys have some Calc 3 experience. So you know what a zero vector is, and if you're in my Calc 3 class, we proved it's the additive identity. We proved there's an additive inverse, right? The negative of the vector. We do all this in Calc 3. I'm going to bank on the fact that you guys have all seen that because you said you did. And that wasn't something that challenged you. Does this have an additive identity? Is 0, 0, 0 in this set? Yeah, how do you know? Because if s and t are both 0, then I would have the additive identity, wouldn't I? Now, the proof of the closure, that's really going to be next day's lecture. We're going to spend a lot of time proving closures. But I'm going to tell you right now, this set is going to satisfy all 10. That's not even an issue. It would actually be an easy thing to satisfy all 10. And it's an exercise, and you should probably do a couple of problems. I don't like spending a lot of time because it's really tedious, and you're not going to do it in general. There's going to be a point in the near future you can look at it and say yes or no. You just get so used to not what makes it work, no, easier, what makes it fail. Remember, in math in general, proving a true statement true can be very difficult, can even be impossible because there might be an infinite number of cases. But proving a false statement is false is generally pretty simple. Right? I mean, think about it logically. If I said something mathematically that was false, you could say, I can find you a simple counterexample. Okay? And a lot of times that's the case. So let me come up with a different set. I'll do vectors. Okay? I have set T, that's the set of all vectors of the form. I'll do something similar to this. x1, x2, 1. Okay? Where x1 and x2 can be any real numbers. Instead of s and t, I used x1, x2. Really the same thing. All right. Well, let's see. Let me grab two random vectors from this set. All right? Let me call maybe vector u will be x1, x2, 1. And why don't we call vector v, how about y1, y2, 1? You okay with that? Because x1, y1, x2, y2 could be any real numbers. So, what is u plus v? That would be x1 plus y1, comma. No problem there. x2 plus y2, comma. No problem there. 2. Now, what do you think? Is this in the set?
No,
Why not?
the third value is a 2.
Well, to be in the set, that third value kind of needs to be a 1. So I'm going to write, I called it t this time, sorry. This is not in t. Therefore, t is not closed. WRT, what does that mean? Anybody ever use that? With respect to, yeah. So, math people use that because we're really, really lazy. WRT, with respect to. It's not closed with respect to addition. Huh, okay. What if I multiplied this vector by a scalar? Or I'm sorry, if I multiplied vector u by a scalar? Well, let's see. K times vector u for any real number k will be kx1, okay, that's cool. Kx2, that's cool. K. For every real number k, that's what I'm going to get. But for every real number k, I'm not going to have a 1 here, am I? I'm going to have every real number except 1. Oh, I'm going to have 1 once of the infinitely many possibilities. So again, it's not in W. So therefore, what would we say here? Therefore, I'm sorry, not W. Gosh, T, not W. I don't know what's wrong. I have W on my brain here. So we'd say T is not closed with respect to scalar multiplication. Now, maybe the easiest one of all. Where do these vectors live ultimately? This is really important. 1, 2, 3. Where do these vectors live?
R3.
In R3. What am I saying? What's the word? W is a
Subset.
subset. Good. That means, or W is contained in R3. That's what that little symbol means. It means it is contained in, W is contained in R3, which means W is a subset of R3. Is the same thing true for T?
Yes.
1, 2, 3. T is contained in R3. Is W all of R3? No. It's a subset of R3. Is T all of R3? Well, definitely not. So when I'm trying to find the additive identity, it has to be the additive identity of the parent set. What is the additive identity for R3? Do you agree the additive identity for R3 is 0, 0, 0? Does everybody agree with that? Is 0, 0, 0 in this set? You already told me yes, when S and T are 0. Is 0, 0, 0 in this set? Well, obviously when x1 and x2 are 0, I still have a 1 in the third position. Is 0, 0, 0 in that set? No, because I don't have a 1 in that third position. So T does not include the additive identity of R3. That's the one that matters because that's where it lives. So T is not a vector space. W is, T is not. Now, what made this fail? If I gave you 100 similar problems, what's the giveaway, do you think?
Everyone doesn't have any variable.
Okay. Glad you said that. All right, I'm going to change the entire problem now. Is this going to be close to addition now? Yeah. Is it going to be close to scalar multiplication? Yeah. Does it have the additive identity of R3? Yeah. By the way, the reason we don't spend a lot of time on the other properties, this is a vector. It can't fail commutativity. It can't fail associativity. Those are vector properties. So even though those are 10 of the properties of a vector space, this is a vector. You can't all of a sudden fail commutativity of addition. But it's the existence of the additive identity and it's the closures that we really concentrate on. Turns out, guess what? This is a vector space. So it wasn't that there was a constant there. Constants are okay as long as the constant is 0. That's always going to be the case. That's what I mean by you will notice something, kind of a giveaway. All right? On the bottom of, I have an 8th edition here, so your page numbers might be a little different. On the bottom of page 163, the author tells you several what we consider really important vector spaces. You're not asked to prove them. You're asked to accept that these guys are vector spaces. Clearly, R2 is a vector space, R3 is a vector space. So why don't I just say Rn? Because it's vectors, right? Rn is a vector space. But it turns out sets of matrices of a particular dimension. So pick any dimension you want. I want all 3x4 matrices. That entire infinite set is a vector space. And it's actually very easy to show all these things. We're going to do stuff next day also. But integrable functions, those are functions that have antiderivatives. Continuous functions over the number line or continuous functions over an open interval are also vector spaces. Oh, that's crazy. And one of my favorite is polynomials. Now, Pn is the set of polynomials of degree n or less. A lot of people get this one confused. It's the set of polynomials that are of degree less than or equal to n. Let's just pick a number for n. N is 2. Okay? P2 is the set of all second-degree polynomials and all first-degree polynomials and all 0th degree polynomials, which mean scalars. P2 is not the set of just second-degree polynomials. Everybody cool with that? So turns out this is one of the most important vector spaces that we're going to look at, this set of polynomials. They're really interesting and really easy to work with. So create some space here. I'm going to give you a new set. Call it set S. S is the set of all things of the form A0 plus A1x plus A2x squared, such that A0, A1, A2 can be any real number. Oops, sorry. And A2 is not equal to 0. In simple English, if A2 cannot be 0, then that means this is the set of all second-degree polynomials. If A2 were allowed to be 0, it would include other things. Agreed? I'm saying no, A1, A2, and A3 can be any real numbers, but A2 can't be 0. So could A1 and A2 be 0? And now I just have something x squared? Sure. So I can have x squared, so I can have x's, I can have constants, but I got to have an x squared. Piece of cake. I'd like to know if this is a vector space. Well, let's take two polynomials in the set. All right, let's call f of x a0 plus a1x plus a2x squared, and let's call g of x b0 plus b1x plus b2x squared. How's that? All right, what's f of x plus g of x? I'll write it like this so it's easier to interpret. So constant plus and what is k times f of x? That would be ka0 plus ka1x plus ka2x squared. Okay, great. Also, I'll do these both together because it's probably easier to do that way. So, of course, this is still a second degree polynomial, and of course, this is still a second degree polynomial, right? Right? Left eye, something's up. Let's start with the second one, it's easier. For every real number k, this is still a second degree polynomial, right? For every real number k? No, Sam? Does it fail? When?
0.
What if k is 0? Then I just get the number 0, which is not a second degree polynomial. Of the infinitely many k's I could have, they all keep it a second degree polynomial except for one, and that's all I needed. Ooh, it's not closed to scalar multiplication. Well, remember, A2 cannot be 0, so there's no tricks there, right? What if what?
A2 equals negative B2.
A2 is 10. What if B2 is negative 10? Oh, did we just find a way to make that fail? Yes, we did. If the lead coefficient of G is the opposite sign of the lead coefficient of F, then those will cancel and will no longer be second degree polynomial. Wow. It usually is. How's that? Usually when you add two quadratics, you get back a quadratic. But can you find a case where you don't? Yeah, if I get just the right canceling. Okay? What about the additive identity? Now, that's a tricky one. What would be the additive identity of the set of all polynomials? The number 0. Not the vector, not the matrix, the number 0. Do you all agree that if I add the number 0 to a polynomial, I get back to polynomial? Okay. Is the number 0 in this set?
If X is equal to 0.
Isn't this the set of all second degree polynomials? Is the number 0 a second degree polynomial? No. The number 0 would have required all my coefficients to be 0, but A2 can't be 0. So this set does not include the additive identity. Whoa. Well, will it be commutative? Yeah, because they're polynomials. Addition's commutative already. Is it associative? Yeah. Distributive property hold? Yeah. All the algebraic properties are always going to hold. You can't all of a sudden fail algebraic properties of algebraic statements. It's the closures and the 0. So I'm going to give you a picture of what we just did that might make it easier to understand. Okay? P2. I want to change this, first of all, to P2. How do I change this to P2? There's one thing I need to change.
Erase A2 cannot be 0.
Erase that. Now it's P2. Now I put no restrictions whatsoever on any of the coefficients, so all of them can be 0. This is a vector space. So would you agree that if I took every constant, put them together with every linear function, and put those together with every quadratic, I would now have every polynomial of degree 2 or less? Here's what closure is. If I took any two elements from this set and I put them together, I get back something from this set. If I take any two elements from this set and put them together, I get the same thing. If I take any two elements from the big circle and put them together, I stay in the big circle. But we just saw that I could take two quadratics and add them and get something that's not a quadratic. So even though the result of two quadratics being added together are still in the big circle, they may not be in this section. They might end up over here. They might end up over here. Oh heck, what if G is just simply negative F? Then I got 0 when I added them. So for a vector space, any two things in the big circle added together stay in the big circle. I took a subset of the vector space, which is actually where we spend most of our time in this class. And when I added those two things together, I didn't necessarily stay in this region. I may have ended up here. I may have ended up here. I'm still in the big circle, but not in that section. That's why my set S is not a vector space. It failed both closures. And in fact, where does the additive identity live? It lives in this one over here. So the set of linear functions in general is not a vector space. The set of quadratics. What about the set of all fourth degree polynomials? Not a vector space. But the set of all polynomials of degree 4 or less is. Okay? Is this complicated algebra? Oh, God, it's trivial algebra. Are your brains going to hurt later thinking about this? Oh, yes. Yes. I suggest a leave. I think that works better than motion. That's my experience. But now, this is very, very abstract stuff, but the notion of vector space is now the most important thing mathematically. Vectors have certain properties. They're clearly listed here. Now, if I remove the word vector and I just say I have a bunch of things, and they have the same properties, and what I mean by properties is that their sum is in the set. That's closure. That their sum is commutative. Their sum is associative. There is an additive identity in that set. There's an additive inverse in that set. Well, isn't that true with polynomials in general? Isn't that true with matrices in general? Isn't that true with all sorts of functions? Those statements I just made? Yeah, it didn't necessarily have to be vectors for those things to be true. That's why we call it a vector space as opposed to a set of vectors. So when you hear the term vector space, it might be vectors. It might be vectors. In fact, we usually start with vectors because it's clearer. But we'll do problems. Probably the most common vector spaces we work with will not be vectors. Probably be matrices, because those are the most useful and practical ones for us. But vectors and matrices, we'll see, they kind of go hand in hand. Well, what about like polynomials and things? Well, it's very powerful to know those are vector spaces. And I'm going to give you a glimpse. I'm going to give you a glimpse. It's a crazy glimpse. I want you to consider all vectors of the form A, B, C, D. Obviously, this lives in our form. All vectors of this form, that's an infinite set. It is a vector space, right? Because I could be 0, 0, 0, 0, okay? I want you to consider all matrices of the form A, B, C, D. This is an element of M2, 2. I'm giving you row, column. I want you to consider all polynomials of the form these vector spaces are isomorphic. And I can easily go from one to the other if I just create the proper mapping. How do you, I tried to make it as obvious as possible. How do you know you can go from one to the other? Are you using the same 4 numbers in each one? So if I defined a map that took you from here to here, or from here to here, or from here to here, and so on, I could do some manipulation, couldn't I? That's kind of the crazy stuff we're going to be doing in this. We're going to be able to go from literally one end of the universe to a different end of the universe, because the conclusions that I make in one might be really difficult directly, but I might be able to find an alternate path. There are entire branches of mathematics devoted to this kind of thinking. We're just going to be exposed to it, okay? But it's really cool stuff. Think dot product. Everybody knows dot product. Turns out dot product, what you know dot product is actually called the Euclidean inner product. There are an infinite number of versions of dot product. The dot product that we know and use in calculus is just one of infinitely many that work. Imagine the rules for dot product if I just for fun put coefficients. You know, u1 v1 plus u2 v2 plus u3 v3. What if I just put coefficients in there? It'd still work. I can still find angles. But what if I said, I took dot product and I said, now I want to do dot product of 2 matrices that are the same dimension. And whatever I got here, I want to kind of make sure I get something similar here, and I can do that. I want to do dot product of 2 polynomials. You see, because everything's in the same position, I can get results. But then that would allow me to take a vector, turn it into a polynomial, maybe do a definite integral and go back. I mean, crazy stuff like that. Completely, I mean, it just sounds completely whacked at first. It sounds like we're making it up as we go. Well, in a sense, we are kind of, but with a purpose and the internal consistency that we're going to show that things have. There are stuff you can do. Entire branches of mathematics, like I said, are based on this kind of thinking. That's why a lot of you have heard this. The most foundational math courses, if you're going to study math, there's 2 of them at Mesa College. This one and discrete. Everything you ever do after is going to be based on those, not on calculus. The only other time, if you're a math person, the only other time you'll ever see calculus again after differential equations, which is still considered lower division, would be in statistics. Because there's a lot of calculus. Everything's calculus based in statistics, but you might not ever study statistics. So if you're a math person, you may never do another integral or derivative as long as you live after you finish differential equations. That's engineering math. That's not bad. I'm just saying that's what that math is for. This spatial reasoning, crazy stuff that we're talking about is where most math is going. But from a number crunching standpoint, it's usually low level. It's not about numerical values. It's about understanding and you know, what can I do and so on. And today is the starting point. This chapter is very abstract. But no part of the chapter algebraically is difficult, and you're not doing any calculus. So it's more, you know, on a daily basis, you're going to get up and say, oh my God, what dimension am I in today? You know? Knock on the wood, is this real? No, we're not going to go real complex till later. You know, then you'll start questioning, right? But you'll have questions, and questions are good. Okay, go ahead and stop. All right.